Good afternoon, everyone. I am from Professor Offer Furstenberg's lab, so I tied my hair so you can see my lab logo. Okay. So I'm going to talk about room temperature probabilistic CNOT gate with synchronized photons. In simple terms, what we are doing is quantum computation using photons. Have you ever wondered how computers make decisions? The classical computers use electronic switches, which are called transistors. The quantum computers, whereas they operate on the laws of quantum physics. So, if we look at the classical computers, they require bits, which is either 0 or 1 to perform computation, whereas quantum computers require something called qubits. And these qubits are a superposition of 0 and 1. So the state can exist both at 0 and 1 at the same time. There are various researchers trying to develop quantum computers, even companies and startups are working on it. So there are different platforms through which we can perform this quantum computing, such as superconducting qubits, trapped ions, neutral atoms, spin qubits, photonic quantum computing. What we are working on is photonic quantum computing. Here, we are using the particles of light, called photons, to perform the computation. They carry and process the information that we need. And we demonstrate a CNOT gate, which is a universal gate. You can use this CNOT along with some linear gates to perform any kind of computation that you need. For the first question that comes to our mind is, why do we use photons in quantum computing? Actually, photons enable us to set up a global network all over around the world. So they help us in long distance transmission. And since these photons are weakly interacting with the environment, they help us set up a low loss transmission. And these photons can be transferred through or transmitted through optical fibers and even in free space. So they are compatible with the existing technology we have. The other point is, for computation, we need something called entanglement, which helps us, and we can use the photons to create this entanglement, which helps us in developing a secure communication network. The important point that since it involves the speed of light, so our computation has very high speed, and these technologies are scalable. When we talk about quantum computing, it's just not physics. There are various other fields where we can use this quantum computing. For example, in the field of chemistry, we can use quantum computing to simulate molecular interactions in a very faster way, which helps us in discovery of new drugs. Also, in the field of biology, we can use this quantum computation to analyze the protein foldings, which is very important for biologists. Similarly, there are many other fields where quantum computation is very helpful, such as particle physics, metrology, and much more. One important thing when we talk about computation, quantum computation, is the entanglement. That is the entanglement between two particles. Now let's first understand what is entanglement. Let's say there are two particles and these particles are very far away from each other, and there is no way these particles can interact or talk to each other. So these particles, but they are correlated in such a way that if I perform a measurement in one of them and I know that the state of this particle is this, I can instantly say what is the state of the other particle without even performing any measurement on the other particle. This means that these particles are correlated, are entangled, and this helps us in computation in various ways, which I'm going to explain later. So I'll give you an example. Let's say there are two persons who are sitting in different parts of the world. They are in no way they can communicate with each other, but what they have common with them is a magic coin. And this magic coin is conditioned such that if one of them tosses the coin and gets head as a result, I can immediately say the other person has a tail. I don't even need to ask the other person or communicate with the other person to toss the coin. I can just say that this person has got a tail. So this is what entanglement is. And how entanglement helps is these qubits, they exist in multiple states. So we can, it allows us to perform computation in a faster way than classical computers. And since the information is being shared instantly, so it actually increases the speed of complex calculations. And the Entanglement is also used for error correction in quantum computers. It also helps us to create an ultra-secure communication. So if somebody is trying to breach or break into your data, it breaks the entanglement, and then you know that somebody is trying to breach your data and you can work on it. What we are doing in our lab is we are performing computation using synchronized photons. So what do we mean by synchronization? Let's say I have a source which generates single photons, and these photons are coming probabilistically. By probabilistic, I mean they're coming at random times. If you consider the horizontal axis as a time axis, then you can see all these photons are at different times. So if I want to perform computation, I need them to be coming at the exact same time. But this is not the case with probabilistic sources that are operated at room temperatures. So what we do is we integrate our source with the quantum memory. Now we are storing all these photons into the memory, and we retrieve them or release them whenever we need. So I can send a trigger, and now I can get all the photons coming at the same time. Why is it important to synchronize these photons? I'll give you an example of what we are doing in the lab. We are performing computation using 2 photons. So in that case, if I perform this computation using this probabilistic photons, then per second I can have only 1 pair of photons coming. And let's say to perform this experiment, I need a time t. If I synchronize these photons, then per second I can have 20 counts instead of this 1 count. So that decreases my experimental time by a factor of 20. Think about it, like one of the measurements that we are doing, it takes 7.5 hours to do that measurement. If I do the same measurement with these probabilistic photons, it would take 7.5 into 20, like 150 hours to do the measurement. That's not even practically possible. So synchronization helps us to perform the computation in a faster way. This is a simple schematic of what we are doing in the lab. We have a rubidium atomic vapor, where this is being used to generate single photons from this medium. And also we have another similar rubidium atomic medium which acts as a memory. Since our source and the memory are 2 similar mediums, so the photons that are being generated from the source are very compatible with the memory, and we can easily store them here. So let's see the process. So once I generate a photon from the source, I store it into the memory. Now, when I detect the other photon at some random time, I send a trigger to the memory that you release now the first photon which was stored here. So in that way, I can create a synchronization and I can get both the photons at the same time. So this is a simple scheme of what we are doing in the lab. This is the experimental setup, but it looks very complex. I'm not going to go into the details of it, but what I wanted to show is the CNOT gate is being operated using some linear optical elements, a simple linear optical elements. Now let's try to understand the results of what we are doing. This is the input of the matrix that I'm giving as an input, let's say, to the CNOT gate. So if you look at the matrix, we have 1, 1, 1 in all the diagonal elements. After the CNOT operation, now I see the matrix, and this, if I see the lower 2 elements, these are flipped. So we can understand this. This is the outcome of a CNOT. We can understand this as, let's say we have 2 switches, and these switches are to operate, let's say, the light on or off. You want to switch on or switch off the light. So the first switch controls the operation of the second switch. If the first switch is on, whether the second switch is on or off, the state will be flipped. If it's on, it will become off. If it is off, it will become on. But if the first switch is off, the state of the second switch doesn't change. It doesn't get affected. So this is what happens. In the first 2 elements, the first switch is off. So it doesn't change the state of the second switch. But in the next 2 elements, the first switch is on. So that actually reverses the state of the system. So that's how we get this matrix as an output. This is the ideal matrix of a CNOT operation. Now I want to compare this to my experimental results. Here you can see these green bars are our experimental results, and these yellow shades represent this matrix exactly, which is the ideal matrix. We characterize our gate through a parameter which is called the fidelity of the gate. The fidelity basically gives an estimate of how close our experimental results are to the ideal case. We can see that we have a gate fidelity which is 86%, and this is very high if we talk about the room temperature sources that we are using. One thing that I mentioned in my talk earlier is the entanglement, how entanglement helps in secure communication and faster communication. So we also characterize our performance of our gate by calculating the entanglement fidelity. So what we do is we take 2 photons into the CNOT gate, and then as an outcome, we don't get the individual photons. Rather, what we are getting is a superposition of these 2 photons. And then we similarly calculate the entanglement fidelity, and we are getting a fidelity of 83%. If you think about the room temperature sources that we have, these fidelities are good enough or pretty high. So we conclude that we are able to create synchronization between photons, which helps us in creating multi-photon states. And we perform an all-optical 2-qubit operation, and we demonstrate a universal CNOT gate with high entanglement fidelity. Since this system is a room temperature system, they are easily scalable, they are cost-effective, and can be deployed easily. They are robust. They do not need any cryogenic cooling and complex infrastructure like superconducting or other systems. So our system has great potential to implement for future quantum technologies. I want to thank my supervisor, Professor Ofer Fistenberg, and my lab mate, Haim Nakav, and also the entire Light versus Matter group, and my friends, those who are here to support me. And also, I would like to thank the organizers for such a wonderful conference and giving me the opportunity to talk here.